Okay, you guys, I'm going to start here, different hours, left off at different spots. Most hours we talked about this picture here, but I didn't quite get to it in a couple of my hours, so I'm going to start there. So we had filled out this, and so we had filled out that electrons from organic molecules are first transferred to NAD+, and they're transferred, which means that these guys are an electron acceptor, which means that when NAD plus accepts electrons, remember oil rig accepts electrons, so that means it's being reduced because reduced is gaining. So that's what's going on here. This acts as an oxidizing agent. But really what you need to know is this, that NAD plus is an electron acceptor. And each NADH, which is the reduced form, so that means it gained electrons. NAD plus, when it gains electrons, it becomes NADH. So let's look at that reaction. So really what we're looking at here is for NAD plus to gain electrons, the electrons come from hydrogen, and the hydrogen was on the glucose molecule. So 2 hydrogen from glucose. Each hydrogen has an electron, combines with NAD+, and we're going to end up with NADH plus H+. And so that's what this picture here is showing you. Let me switch colors here. So here's your NAD+ molecule. So this is before it accepts electrons. So I'm going to draw your attention to this part here. It says N+. The plus means that how does something become positive? It lost an electron. And so that's why it says here that this is in the oxidized form. Oxidized is losing electrons, so this has been oxidized. This whole molecule is NAD+. The part that's important in this reaction up here is this part here, which is why it's kind of boxed in here and is in white. So that's the important part. So this is going to be reduced or gain electrons. We're going to strip the electrons from glucose. So that's where it says here 2 hydrogens from food. So what's the food? It's C6H12O6, glucose. So let's talk about a hydrogen atom and review a hydrogen atom. Hydrogen has 1 proton in the nucleus, so it's 1 proton in the nucleus, and then spinning around that, it has 1 electron spinning around that. So this is 1 hydrogen. And so now we said we had 2 hydrogens, so I'm going to draw that again. 1 proton and electron move spinning around there. All right, and orbiting around there. So that's your hydrogen. And we said that this is going to become reduced or gain electrons. So the electrons that it's going to gain are from glucose, but where in glucose? It's from the hydrogen in the glucose molecules. And so 2 out of those 12 hydrogens we're looking at here for 1 NADH. And so we can think of hydrogen. Notice that it says here, there's this arrow here. It says 2 hydrogen are really 2 electrons and 2 H pluses. H pluses are a hydrogen atom that has lost an electron. So here we have 2 hydrogen. Each one of them has an electron, so that's your 2 electrons. And then if we don't count the electrons, the hydrogen without an electron are 2 H pluses, or really just a proton, so that's the 2 H pluses there. So these 2 are going to react. So that's the beginning of your reaction. Notice here that we have dehydrogenase. ACE means it's an enzyme. So this is an enzyme catalyzed reaction. This enzyme is going to help this reaction occur. So then what happens at the end of the reaction? So remember that NAD plus is going to accept electrons. And so where do those electrons come from? They come from the hydrogen. So if we look here at this box here, notice that we now end up with NADH. NAD plus has become NADH. And so so it has been reduced. This is the reduced form right here. It's reduced, which what does that mean? It has gained electrons. So where did the electrons go? How did it gain electrons? So if we look at here the 2 hydrogen, That's where the electrons came from. If we look at the NAD+, notice here the nitrogen had a positive charge. Now the nitrogen doesn't have a positive charge. How did it get neutralized? One of the electrons from hydrogen neutralized that nitrogen. So therefore, NADH is carrying one electron that was part of the hydrogen of food in this nitrogen atom. And then look at here, this atom, this carbon atom at the top here had one hydrogen attached to it. Now it has a second hydrogen attached to it. So therefore, this whole hydrogen, this whole second hydrogen is attached there. That hydrogen has an electron. So now we have NADH having two electrons, or carrying two electrons that were once from food. Now look at here, this little guy he lost an electron to the nitrogen, so now he doesn't have an electron, so now he's the hydrogen ion, he's H+, which is why we have an extra H+ at the end, that's not used in the reduction or the gaining of electrons of NADH. So NADH carries two electrons that were once part of glucose. So this is an electron carrier. So why is it NADH and not NAD+? So it got rid of the positive when the electron from one of the hydrogens neutralized the nitrogen. So now there's no positive charge, it's neutralized. And the H comes from the second hydrogen, so it's NADH now. So it's carrying two electrons, one here and one here that was once part of hydrogen. This is going to become important as we go on in cellular respiration. So we have these electron carriers, and so throughout the process of cellular respiration, we strip or take these electrons out of the hydrogen that was once part of glucose. And these electron carriers are going to use those electrons and drop them off later on in a certain step of cellular respiration. Those electrons are going to be instrumental in making our glucose. So NADH passes and what does it carry? It carries electrons to the electron transport chain. This is going to be really important later on in making ATP. So like uncontrolled reactions, the electron transport chain passes electrons in a series of steps instead of one explosive reaction. So we get more energy by slowly stripping the hydrogen and the electrons off of glucose than if we did in one big reaction, kind of like with gasoline. Gasoline is a fuel, and we can burn it and get more energy out of it to do work by burning it slowly like we do in cars than we would if we took the same amount of gasoline and threw a match on it. We would get a huge explosive reaction and we'd get lots of energy, but that energy wouldn't be available to do work. So that's the same kind of concept as burning glucose. So what happens is glucose is broken down in the presence of oxygen, and oxygen plays a big role. Oxygen pulls the electrons down the chain in an energy-yielding tumble. Oh, the announcements are coming on.
One more thing I forgot.
Okay, so oxygen pulls electrons down the chain in this energy-yielding tumble. So what happens is these electrons, NADH is going to carry these electrons to the electron transport chain, which is a series of molecules that the electrons are going to be transferred from one molecule to the next. And this energy that's released from the electrons moving from one molecule to the next is going to be used to make ATP, to regenerate ATP. So if we look at the next picture here, it shows you that. So here is an uncontrolled reaction. So basically, in cellular respiration, you have, C6H12O6, you have glucose. But remember, we're taking the hydrogens and getting the electrons off of the hydrogen. And then that reacts with oxygen. So we have oxygen and we have hydrogen with their electrons that we're talking about here. So if we in the lab were to take hydrogen and oxygen and combine them into water, that's a very explosive reaction, and that releases lots of heat and light energy, but not a lot of energy to do work. Essentially, in cellular respiration, we're doing the same thing. We're stripping the hydrogen and taking the electrons off of the hydrogen of glucose, and it's going to meet oxygen, and we don't want a big explosive reaction, so we want it to release a little bit of energy at a time. So what we have here, this right here, is the electron transport chain. And so notice here, if we take 2 hydrogen from the food, and remember NADH is kind of carrying those electrons, those 2 electrons from the food, and it says a half of an O2. That's because, oh no, my lights just went out. Okay, so that's because one oxygen reacts with 2 hydrogen to make an H2O molecule at the end. O2, in real life, this would happen, there would be 4 hydrogen reacting with 1 O2 molecule, but we're going to look at it as 1 right now. So that's why it says a half of an O2. A half of an O2 is just 1 oxygen to make 1 water molecule. So what happens is, remember that that NADH was carrying 2 electrons. And so here are those 2 electrons right here. And so so we have the 2 electrons. The electrons leave, so NADH carries the electrons to this electron transport chain. It has a series of molecules in it. And what happens is the electrons go from NADH that was carrying them to the next molecule, to the next molecule, to the next molecule, because as we go down the electron transport chain, each molecule is more electronegative than the next one. And that means it draws electrons towards itself. And so therefore, when the electrons leave NADH and go to the next molecule because it's drawing it to them, then it goes to the next molecule because it's more electronegative and drawing it to it, and so on and so forth, till eventually the 2 electrons get at the end of the electron transport chain, and the oxygen right here is the most electronegative. It's more electronegative than anything in the chain. And we call this the final electron acceptor, because the electrons, that's where the electrons that were once in glucose are going to end up. And so the 2 electrons combined with the 2 H pluses that were, remember, a hydrogen is electron and a proton. And so so when we took the 2 hydrogens to make NAD+, those we separated the 2 electrons from the 2 H pluses. They come back together in the end and form, again, 2 hydrogen atoms, and then 2 hydrogen atoms. So these 2 combined, these guys are 2 H's, 2 electrons, 2 H pluses. The 2 hydrogens combined with the 1 oxygen makes a molecule of water. And remember, this was waste. This is, we talked about yesterday, that we breathe that out, all right? And so, so what's the purpose of this? The purpose is that these are a series of redox reactions. So what happens is that when NADH gives electrons to the first molecule in the electron transport chain, this molecule, so when it gives up the electrons, to this first molecule gains electrons, so it's reduced. Remember, oil rig. So this is reduced, and NADH becomes NAD plus again and becomes oxidized. And so then this molecule gives the electrons to this one, which then this one becomes reduced, and this one becomes oxidized. And so as the electrons move down the electron transport chain, this is a series of oxidation reduction reactions. When that happens, those are exergonic reactions that release energy, and that energy is used to make ATP. So therefore, these small little transfer of electrons from molecule to molecule is that series of steps that makes it not one big explosion, but a little bit of energy released at a time to generate and make your ATP. And so that's how we get the most out of our glucose, is in that way. All right, so that's your background information about cellular respiration. So let's talk about the general overview of cellular respiration. So there are a few stages of cellular respiration. There's 3 of them. The first one is glycolysis, the second is citric acid cycle, and the third is what we call oxidative phosphorylation. So glycolysis breaks down glucose into 2 molecules of what we call pyruvate. So we're beginning the breakdown of glucose and beginning to take off the hydrogens and the electrons in the hydrogen, making NADHs. The citric acid cycle completes the breakdown of glucose. So what happens is glucose is broken down by the second stage. So why do we need this third stage? This third stage is where most of the ATP is made. It counts for most of ATP synthesis. In oxidative phosphorylation, the electron transport chain is part of that. So we already talked about the electron transport chain, so let's just write that here. So the electron transport chain is part of this process called oxidative phosphorylation. And so this is the process. This is the electron transport chain. This is oxidative phosphorylation, this series of redox reactions releasing ATP or releasing energy to make ATP. So the process that generates most of the ATP is called oxidative phosphorylation because it's powered by redox reactions. So let's look at this, these 3 steps here. And so this is our overview. So the first step is glycolysis. Glycolysis basically takes glucose, which is a 6-carbon molecule, and breaks it down into 2 pyruvates. The pyruvates are 3-carbon molecules. So we start to break it down here. This is the first step in which we start to strip the glucose, the hydrogen, and along with the electrons that they carry, strip it from glucose. And so notice here it says electrons carried via NADH. So we're making some NADH, which are those electron carriers. Notice that these electron carriers take the electrons to that third step, and that third step is where the ATP is going to be made. And remember, the electrons go down that electron transport chain, releasing energy to make ATP. So the purpose of this first step is to generate and make NADHs to be used in that third step where most of your ATP is made. Notice that some ATP is made, but not a whole lot. And it's made by a process called substrate level phosphorylation that I'll talk about in just a second here. Then, that's the first step. So then the second step is the citric acid cycle. So the 2 pyruvates now enter the mitochondria. So notice that the first step of cellular respiration doesn't even occur in the mitochondria, it occurs out here in the cytosol. But to finish cellular respiration, the rest of it occurs in the mitochondria. So the 2 pyruvates enter into the go to the citric acid cycle. Notice here the citric acid cycle, we wrote up here that it completes the breakdown of glucose. So by the end of this cycle, which means, what does a cycle mean? What enters it goes through a series of reactions, and then you end up with the same molecule at the beginning, at the end that you had at the beginning, and this keeps rotating round and round as more enter. And so it continues the breakdown of glucose. So by the end of this, glucose is all broken down, and so we've stripped then all the glucose of all the hydrogen and therefore its electrons off of there. So notice here that there's another arrow that comes up here going to oxidative phosphorylation, and it says electrons carried via NADH, so that's an electron carrier, and we'll learn later on when we talk about the citric acid cycle that there's a second electron carrier called FADH2, and so they both carry electrons to the electron transport chain in oxidative phosphorylation to move down the electron transport chain to generate ATP in this third step. So that brings us to the third step, oxidative phosphorylation, which is in part electron transport chain, and chemiosmosis is the actual process of actually making the ATP. And notice that this explosion is bigger than the previous two. The previous two steps make a little bit of ATP, but the amount of ATP that is made in the first two steps would not be enough to keep our cells alive. So really, the bulk of the ATP is made in this third step, and that's what we want to get to, our cells need to get to get the majority of the ATP. So then what is the purpose really of these previous two steps? So the purpose of these steps, let's write, whoops, so you can see here, purpose of these two steps is to make NADH the electron carriers and FADH2. So that's the purpose of these guys. And so these guys make the electron carriers so that then the electrons can get to the electron transport chain in the third step, and that they use those electrons. The purpose here isn't to make ATP. So that's the important step we need to get to, but we can't get to that step unless we do the other two steps, which strips the electrons that are going to be used in the electron transport chain. All right? So in this case here, so this next bullet, oxidative phosphorylation, accounts for almost 90% of the ATP generated by cellular respiration. So that's why it's real important to get to this last step, all right, to do that. A small amount, though, of ATP is formed in glycolysis in the citric acid cycle, like I said, but not enough to keep our cells alive. And so the way that this is made is by a process called substrate level phosphorylation. So what does this mean? It means that the phosphate group that is used to make ATP comes from another molecule, a substrate. So here's an enzyme. Here's the substrate. Notice the phosphate group on the substrate. So in this case here, this is the enzyme's active site. There are two things that combined here, ADP and the substrate with the phosphate group. So what does this enzyme do? It puts stress on the bonds that hold this phosphate group to this molecule and causes the phosphate to come off, and it puts the phosphate onto ADP to make ATP, and then we have our product without the phosphate group. And so that's how ATP is made in those first two steps, is by taking the phosphate group off of another molecule, right? And that's called substrate level phosphorylation. So we'll see that in glycolysis here. So glycolysis is that first step. So now we're going to look at just this first step. What happens? The big picture, glucose gets broken down into two 3-carbon molecules called pyruvate. Some NADH is made, a little bit of ATP is made. And so we'll talk about this and then we'll call it a day here. So glycolysis literally means the splitting of sugar. So remember, we are splitting. We're going to from a 6-carbon molecule to 2 3-carbon molecules. So it breaks down glucose into 2 molecules of pyruvate. Where does this occur? Let's go back to here. It occurred not in the mitochondria. It occurs out here in the cytosol or cytoplasm. And there's 2 major phases, what we call the energy investment phase. Energy investment, meaning you're using energy. What's our energy molecule? ATP. So in this case, ATP is needed. And then there's the energy payoff phase, which means that we invest a little bit of ATP, and guess what? We make a little bit of ATP. That's the payoff. And I'm going to put in parentheses that why it pays off is that actually more is made than what was needed. So I'm going to put here more than what was needed. And that's why it's a payoff. So it's beneficial for the cell to actually expend a little bit of energy to actually get some energy, a net increase in ATP. So let's look at this down here. So this is the big picture here. So there's 2 phases. And so notice here, let's look at the beginning. So remember glycolysis, we're taking glucose and breaking it into 2 pyruvates. So here's the beginning, glucose, going to go through a series of reactions, and this is the end, right? So this is the end, and this is the beginning. what happens in this? So there's two phases. The first phase is called the energy investment phase. So that's when ATP is needed. And then the second phase is the energy payoff phase. So this part right here is the investment, this part right here is the payoff, and here's our end. So let's look at these. The energy investment phase goes through a series of reactions. This arrow, they're not showing you here, they're just showing you just general overview. There is a series of reactions that occur, and to cause glucose to change shape and so on, and for these chemical reactions to occur, ATP is used. So what does that mean when we use ATP? So this arrow is showing you that ATP goes into the reaction, and when it's used, we break it down. What happens when we break it down? It breaks down into ADP and a phosphate. So therefore, that's an exergonic reaction. So what happens is the energy is used in the reactions in this energy investment phase. So notice that there's 2 ATP needed in the first set of reactions. Then in the second set of reactions, look at what happens then. Second set of reactions, we have an arrow here, and 4 ATP are formed. So we wrote up here that we get more than ATP than was needed. So 4 is more than 2. So we gained a net of 2 ATP in this next series of reactions. And so how do you make ATP? If you need 4 ATP, you need 4 phosphates and 4 ADPs. And so that's what goes in, and we get 4 ATP formed. Then also, in this energy payoff phase, remember glucose is starting to be broken down and is eventually going to end up as 2 molecules of pyruvate. We're going to strip the glucose of a couple of some hydrogen along with their electrons. So what happens is we end up making 2 NADHs. And so remember, each NADH carried 2 electrons. So we have 4 electrons being carried there. So how do we get 4 electrons? We used 4 hydrogen that was once part of glucose. So 4 electrons and 4 hydrogen, or 4 hydrogen ions constitute 4 hydrogen atoms. So we stripped the molecules that used to be glucose, as we're going through these series of reactions, of 4 hydrogen, making 2 NADHs. And each NADH is carrying 2 electrons. All right? And so what we end up with is our net gain. So what do we get out of glycolysis? We end up with 2 pyruvates and 2 waters. That's part of the waste products. We get 2 ATP. This is the net. So notice there we formed 4, but we had to use 2 to begin with to get those 4. So we don't count those 4 as really gaining 4 ATP. So 4 minus the 2 used gives you a net of 2, and then we get 2 NADHs. So when we're looking at what comes out of glycolysis, going back to that big picture, here we have the 2 pyruvates that are going to go now into the mitochondria. We have our 2 NADHs, and we have our 2 ATPs. So now we can add some numbers in front of this. So we can add a 2 here. We actually get 2 ATP and 2 NADHs according to this. All right? And so looking at, let me get this energy investment phase. So let's write here that this is a series of reactions. And I'm going to put here C figure 99A. And then this is C figure, and it's the second part of A, C figure 99B, the second part of B. All right, and so we're going to look at these. So these are, I'll put here that this is a series of reactions to the energy payoff. So when we look at let's write that this is waste. And this is going to go to the electron transport chain. In the electron transport chain, I'm going to start abbreviating as we write this, ETC. And so that's this picture here. So NADH leaving glycolysis and going to the oxidative phosphorylation in the electron transport chain. Okay? So when we look at this next picture, when I said we're going to cross off this, so this is what we want to look at here. So notice here 99A2. So when I said here, see figure 99A2, this is the more specifically what happens in the energy investment phase. So this part right here, let's label this the energy investment phase. And so really what we're going to get here, all right, is notice here, this is your beginning. What enters at the beginning is glucose. So this is your glucose molecule right here, C6H12O6. So we don't need to know all the intermediates here, but I just wanted to show you that it is a series of reactions. So when I said over here that we go through a series of reactions right here and that 2 ATP are used. So this is that series of reactions. And notice here that here is the ATP and here is the ATP that's used. So here are your 2 ATPs used. And what happens when you use them, it breaks down into ADP and a phosphate. And the phosphate groups, so that's what, when you see an arrow like this going in and out, that means ATP comes in, ADP comes out. That's what that means. And so it's used, so ATP is used in this reaction from here to here. And the phosphate group actually goes on to here, it phosphorylates it. All right, and so the same thing here. So we have another phosphorylation. And so what you end up with at the end, so basically you just need to know that 2 ATPs are used in this series of reactions, and at the end of the energy investment phase, you end up with 2 molecules. Notice here that the arrows go back and forth between the two. These two can go back and forth between each other. And so what does that mean? They're made in equal amounts, but what happens is only one of them goes to the next phase, which, remember, the next phase, if we go back over here, the next phase is the energy payoff phase. And this is the only one that does that. And this is called, it says glyceraldehyde 3-phosphate. They abbreviate that G3P. Instead of saying that all the time. So even though these guys are made in equal amounts, this one is going to go to the energy payoff phase. So the next series of reactions, this doesn't. So what happens is, as this one leaves, this one is converted to this one. So then really, by this enzyme here. So what at the end of the energy investment phase, ultimately you end up with 2 molecules of G3P. All right, so that's your energy payoff phase. So really then the big picture of the energy payoff phase is you end up with a glucose being broken down into 2 G3P molecules. This is a 6-carbon molecule. These are 3-carbon molecules, and you can count the carbons there. All right, and so that's the energy investment phase. That used 2 ATPs. So this used 2 ATPs. So now what happens is these G3Ps are going to go into the energy. If we look here, it's back to where we wrote here. What happens next? The energy payoff phase. And then we're going to end up with the 2 pyruvates. So if you look at the next picture here, I'm going to have you cross off, again, this picture, and just look at this one. Notice here, 99B2, if we go back to that overview, I put here for the energy payoff phase, see figure 99B2. And so that's what we're looking at here. So this right here, we're going to write, is the energy payoff phase. And so what happens here? What enters? And so what is entering here is the G3P. So the G3P enters into this. So that enters. And this was from the energy investment phase. Now, how many do we have? 2, right? And so this happens twice, once for each molecule. So that so that's what we have here. So notice here that as the G3P enter, we get NADH is made. So we get 2. So we have the 2 NADH made. How does that make? The NAD plus comes, and we're going to strip two hydrogen for each NAD plus. So we're going to have 4 hydrogen coming off of G3P, which used to be glucose, and make your NADHs. Each NADH is now carrying 2 electrons that were once part of glucose. Then we get, notice here, 2 ATPs. So we in each one of here. So we get 4 ATPs made, correct? All right, 4 ATPs made, and so we have a net gain of 2 ATPs, right? Because in the first phase over here, we had to use 2 ATPs. Now we get 4 ATPs, and so we have the net gain of 2. And so that's why it's the energy payoff phase. And then we have a little bit of waste. So here's your 2 waters, and that's your waste coming off of there. So what do we have at the end? We have pyruvate, all right? And then there are 2 of those, all right? 2 pyruvate at the end, all right? So this is happening for each G3P. And then we get our 2 pyruvates. So therefore, we get, going back to this, the overview, going back to this picture here. So we just talked about glycolysis and how we ultimately get 2 pyruvates at the end. We get our 2 NADHs that are going to carry electrons to that last step where most of your ATP is going to be made. And we get a little bit of ATP energy. And so what you get to look forward to tomorrow is that what happens to that pyruvate as it enters the mitochondria. All right, so we'll pick up there tomorrow. Have a good night.